Ladies and gentlemen, welcome back to lesson 14.1 in group theory. This lesson, as I promised in last lesson, I'll be giving the proof of the proposition and the theorem that we've seen in lesson 14, the quotient group. The proposition that we've seen talked about how we can get a set and divide this set up into cosets of equal cardinality, which are disjoint. And the theorem, which is very important, talked about how 5 statements about the normal subgroups and the quotient group are equivalent. Before we get into the proof, I'd like to direct your attention here to this drawing I've made that is very similar to the drawing I've made in the previous lesson, except that here I've taken some elements from the original group G and some elements from the coset, the quotient group, if you will, H. So in the group G, I have that two elements A times B multiplied together will give their product naturally AB, which could lie in a different coset or could lie in the same coset as either A or B. Now, the cool thing here that I'd like you to notice that if we take the coset AH, which by the way is taken to be with a representative of A, it could have been taken with any other representative, but I chose A. The cool thing here is if I take this coset multiplied with the coset of BH, I will end up exactly in the coset where AB lies on. So you can see, even though we've collapsed the whole group into a lower resolution group, the structure remains intact. We do not stray away from the structure once we collapse things. And this is the operation that I'd like to prove that it's well defined in our proof. So let's get started. Let us get started with the statement of the proposition concerning coset partitions. Let G be a group and H a subgroup of G. The first result says that if A and B are two elements in G, then either the coset AH is equal to the coset BH, or the intersection of AH and BH is completely empty. The second result says that every element G in G is an element of a unique coset. So not only does every element belong to some coset, it belongs to only that coset. Number 3, there is a bijection between the subgroup H and the coset GH no matter the choice of G. In particular, the cardinality of GH is always going to be equal to the cardinality of H. The number of elements in GH is always equal to the number of elements in H, giving us a new meaning to quotient. It is new but also familiar, because a quotient is what exactly? Consider this example you've taken in elementary school. If I had 6 ice creams and I wanted to share it up with 3 friends, then each friend would get 2 ice creams. So each friend would contain an equal number of ice creams, right? That is exactly what is going on here. We have our group G, we're doing our cosets, and then each coset will contain an exact number of elements as the subgroup H, giving the meaning of the quotient group. The proof of the first part of the proposition is going to be left to you as an exercise, because this proof is done actually in discrete mathematics. It's a standard proof that has nothing to do with groups. It's more general than that. Any set where you can define an equivalence relation and you get equivalence classes, these classes are going to partition the set. The second part of the proof will be done directly. We will prove that G belongs to some coset, and then we'll prove that G belongs to only that coset and no other distinct coset. So G belongs, so let G be an element in G. The most natural choice for the coset where G belongs is GH. So we have that G belongs in GH. Since H is a subgroup, so the identity of G is contained in H. If we perform algebra, we multiply G on both sides. This yields us G is in GH, completing this small part of this proof. Now, suppose that G is an element in another coset which is called KH. We want to prove that KH now is equal to GH, thus proving that G belongs to a single unique coset. Since G is in KH, that means G is equal to K times some H in H. And now we can say that we have that GH is equal to KH H. And if we look here, we can use associativity by saying this is equal to K times HH. So this is a coset called HH, but HH is equal to H because this is essentially equal to H times H star for all H star in H. But this is just equal to H because H is a subgroup. So it's closed under multiplication. So we have that this is included in H. And of course, if we take H star to be the identity, we'd have H is included in that. So we would have a double inclusion and an equality. So this is just equal to KH. Thus proving that GH is equal to KH. The proof of the third part of the proposition will also be done directly. We will find this bijection between H and GH. So let the map phi taking an element from H, giving back an element in GH. So it takes H, and the most natural bijection that we can find is just multiplying G by the element H. We will prove now that this is indeed a bijection. A bijection is a map that is well-defined, injective, and surjective. So phi is well-defined since if H1 is equal to H2, then we can multiply both sides by G, and this is equal to phi of H1, and that is equal to phi of H2. So we just succeeded this statement for all H1, H2, and H. That is done. Now, phi is injective. Injective meaning if we have H1 and H2 in H such that phi of H1 is equal to phi of H2, then we want to prove that this is necessary, implying that H1 is equal to H2. But this is just necessarily GH1 is equal to GH2. And performing some algebra, left-hand side, right-hand side, multiplying by G inverse, we get rid of that G and we're left with H1 is equal to H2. So proving this result for injectivity. The last thing is that phi is surjective. Surjective meaning that for any element in the codomain GH, this element is the image of some element in H. So for all K in GH, by definition of this coset GH, we know that K has to be equal to G times some element H in H. K is equal to GH for some H in H. Okay? And now we have that this exactly means the image of H by phi. And so this is an element of the image of phi, thus proving the surjectivity of phi and thus proving that phi is a bijection, and in particular, so this means that phi is a bijection, and the cardinality of GH is equal to the cardinality of H, completing the proof of this proposition. Now that we've warmed up, it's time to get into the nice theorem about normal subgroup characterization. I'll be restating the theorem now. Let G be a group, H a subgroup of G, then the statements 1 to 5 are all equivalent. That means if you prove one, you've proved all the rest. One implies the other, no matter which way you go. Okay, statement 1. We have that the coset GH times the coset KH is equal to the coset GKH for all GK in G. Number 2, we have that the GH set of cosets is a group. Number 3, we have that H is the kernel of some epimorphism. Number 4, we have that H is closed under conjugates. That means that for any G in G, for any H in H, we have that the conjugate of H by G is an element in H. And number 5, H is a normal subgroup of G. That means that the left coset and the right coset of H by G is equal for all G in G. Let's get started with the proof. Okay, for the proof, I will be starting at the first statement, I'll prove the second statement, and then I'll start from the second statement, I'll prove the third statement, and so on. I suppose this, and I prove that. And at the end, I'll suppose the fifth statement, and I'll prove the first statement. And this will complete the entire proof, because now I can get from any statement, assuming that, and then I can get to any other statement amongst these 5. So, to suppose the first statement, we will suppose that GH times KH gives us exactly the coset GKH. And what I want to prove is that the set GH is a group. Recall that this is the set of cosets of H by the elements G in the group. So, to prove that it's a group, I need a set and an operation. The set is given to be GH. The operation I will define as follows. I will use the very natural supposition here to define my operation on the cosets, which are the elements of GH. So, I will define for GH the group operation star by GH star KH is defined to be just equal to the coset of the product of G and K by the group operation of G, H, here. So this is my definition. I want to see, first of all, that it's well defined. And the reason it's well defined is because I have supposed that one is true. So, once having supposed that, it is, of course, well defined. So, well defined, that is done. Now, I'd like it to be closed under the operation. I'd like to be associative. I'd like to find the identity element and the inverses for all of the elements in the set of cosets GH. So, it's closed under group operation because GKH is an element in GH. It is a coset after all because G times K is an element in the group. So an element in the group times the subgroup H gives a coset, which is an element in GH. So it's closed under the group operation. Next, we have associative, because if we let G1H, G2H, G3H be some cosets, we have that G1H, G2H times G3H, that's just equal to G1, G2H by the definition. G3H, and that is equal to G1, G2 times G3H, using the definition again for the product G1, G2, and G3. And now I can use the associativity of the group itself to say this is equal to G1 times the product of G2, G3, H. I can use the definition of the coset multiplication again to say this is equal to G1H times the product G2, G3H. This is again by the definition G1H times G2H, G3H, thus proving this operation is associative by virtue of the associativity of the group operation. Now, what is the identity element? It is natural to assume the identity element is H because we have cosets GH. So it is natural just to replace G by the identity. And this is 1H, but 1 times any element in the set. So this is just equal to 1 times H for H and H. That's just equal to H. So this is the identity of this group that we're trying to prove. Because H times any GH will give back 1 times GH, which is equal to GH, and GH times H will be also G times 1H, which will give us GH. So it is indeed an identity, and we have inverses. For all G and G, the inverse of the coset GH is equal to the coset of the inverse of G. And the reason is because if you multiply these two together, you get back the identity element H. So if we do that, we get GH times the inverse. By definition, this equals to G times G inverse H, which is just 1H, which is H. And if we do the other way, G inverse H times GH equals G inverse G times H, which also equals to the identity. So we just proved everything we need to say that this is a group. So the set of cosets G/H is a group, which we call the quotient group of G by H. Now they have proved that the quotient set is actually a quotient group. We want to prove that H is a kernel of some epimorphism. So this epimorphism is nothing but the natural projection or the collapsing of the elements onto the line that we've talked earlier. This projection is given by psi. Psi takes an element from the group G and gives a coset. So exactly, taking G here and giving GH. So all what it's doing is that it takes an element from the group and it collapses it onto the coset here. We want to show that psi is a well-defined homomorphism that is surjective, and the kernel of this psi is equal to H. So psi is a well-defined map. Because if we have G1 is equal to G2, we want to be able to say that G1H is equal to G2H. So we're going to use some algebra for that. multiplying G2 inverse on both sides, we get G2 inverse times G1 is equal to the identity. But H is a subgroup, so it definitely contains the identity of the group. And now, performing some algebra again, we multiply both sides by G2 to get that G1 is an element of G2H. And because G1 belongs in the coset of G2H, this is equivalent in saying that G1H is equal to G2H. Because we've said that if two elements are in the same coset, then the coset of G1 and the coset of G2 must be equal. This we've done before. So psi is not only a well-defined map, but it's a homomorphism. And this is where this assumption is very important. It's important for a homomorphism to be a map between groups, not sets. So this is a group, and now using this supposition here, this is a group as well. So it is a map between groups, and it's a homomorphism. It's a homomorphism because we have that psi of G1, G2 is by definition G1, G2, H, but using now the group operation of the quotient group GH, we can say this is equal to G1H times G2H, but this is just equal to psi of G1 times psi of G2, thus proving that psi is indeed a homomorphism. The next step is to prove that psi is surjective, which makes it an epimorphism. So psi is surjective because for all k, a coset in GH, k is equal to G times H, because any element in GH would have this form, G times H for some G in G. And now this is exactly, by definition of psi of G for some G in G. And this is an element of the image of psi. So, to conclude, every element in GH is the image of some element in G, naturally, because GH came from a G. And now the last step is to show that the kernel of this epimorphism is exactly equal to H. So prove that the kernel of psi is exactly equal to H, thus proving the third part of the theorem here. So the kernel of psi is equal to all the elements G in G, all the elements in my domain, that psi maps to the identity. What is the identity of the group GH? We've already said that this is equal to H. Now, this means that this is the set of all G in G such that, okay, what is the psi of G? Psi of G is GH. So GH is equal to H. Okay, so what does this mean? What does GH equaling H mean? Well, if we think about it like this, 1H, we know that this equality essentially means, so if we have AH is equal to BH, this essentially means that A inverse B is an element in H. That's exactly what I'm going to do here with B being G and A being 1. So this is equal to the set of all G such that 1 inverse times G is an element in H. But 1 inverse is just 1, and 1 times G is just G. So it's all the elements in G that are in H, which means that it is equal to H. So we just proved that the kernel of psi is H. So before we move on to the next part, I'd like to just stress out what we just did. We proved that if H is a subgroup which satisfies the fact that GH is a group, that means H is a kernel. So this means that if we succeed in proving that H is a normal subgroup, and then we succeed in closing this hole by proving that normal subgroup implies this operation, this means that this will completely characterize all of the normal subgroups as kernels. So we will be able to say that a normal subgroup is exactly a kernel, and a kernel is exactly a normal subgroup. All the kernels are normal subgroups, and all the normal subgroups are kernels of some homomorphism. Heck, some epimorphism. So let us now prove 3 implies 4. 3 was that H is the kernel of some epimorphism. And in 4, we want to say that H is closed under conjugates, which means that this statement is true. So we need to let G be some element in G and H be some element in H, and we want to prove this is true. Let G be in G and H be in the subgroup H. We have that GHG inverse is an element in H, which, by the way, it's the kernel, as we have proven now, of the epimorphism psi. Psi, as you may remember, is the epimorphism taking an element in G and giving a coset GH. And we've just said that H is the kernel of that epimorphism. So this is if and only if. So since this element is in the kernel of psi, then if we apply psi on this element, we should get back the identity of the quotient group. So psi of GHG inverse should give us the identity, which is H. And because psi is a homomorphism, we can split up this here to get psi G, psi H, psi G inverse is equal to H. But psi of H is nothing but taking H and giving us HH, which we've said this is equal to H. So psi H is equal to H. And because H is the identity, if we multiply the identity by whatever, it just disappears, right? The identity gets absorbed. And this gives us psi G times psi G inverse is equal to H. Now we can use the property of homomorphisms again to combine these two and get psi G inverse is equal to H. And this means that this is psi of the identity of G giving us H. But psi of the identity gives the identity because we've seen a property of homomorphisms that they carry identities to identities. So the identity is H, so this is H equals H. But H equals H obviously is true. So since this is true, then we follow the series of steps backwards to say that this is obviously true. And now we've proved that H is closed under conjugates because any conjugate is an element of H. Now it's time to assume that H is closed under conjugates and to prove that H is a normal subgroup. So a normal subgroup is one where left and right cosets are equal. So we want to do exactly that. Let G be an element in G and H be an element in H. We have that GH, so I'd like for GH to be an element in HG. And if I succeed in doing that, then I would have succeeded in saying the coset GH is contained inside the coset HG. And if I also succeed in saying that the coset HG is in the coset GH, then by double inclusion, I can say they're equal and proving that H is a normal subgroup. So GH is an element in HG. Why? Because GH can be written as GH, G inverse, G. And now that I have appeared the GH, G inverse, this is a conjugate. And what I've supposed here is that any conjugate, GH, G inverse, is an element in H. So because of that, this here is an element in H. So this is in HG. Well, formally speaking, this is like that because I multiplied this by that. And then I use associativity. And then I can say that this conjugate here is an element in H multiplied by G. So this is an element of the coset HG, the right coset HG. So this means that the left coset is contained in the right coset. So by a similar argument, the right coset is contained in the left coset GH. And so this means that left and right cosets are equal for all G in G. It's important that our element G is arbitrary for all G in G, thus proving that H is a normal subgroup of G. The last step in the proof of the theorem is to assume that H is a normal subgroup and to prove all the way back the first statement in the theorem, which is GH times KH is exactly equal to GKH. I want to be able to prove that. So to prove that, we say let G and K be elements in G. And then I just directly compute GH times KH. I find that GH times KH is exactly equal to G parenthesis HK parenthesis H. And this, I can use now the fifth statement to say that HK is equal to KH because H is a normal subgroup. So this is equal to KH, H. And this is equal to GKH. Now, why is that true? You need to be careful here with the subtleties of what I'm writing here. So GKHH, what is that exactly as a set? So here what I'm doing is I'm taking an element from G, I'm taking an element K times H. So this is equal to the set G times K times H1 times H2 for some H1 and H2 in H, right? With brackets here. So I can use associativity of the group to say this is GK times H1, H2, where H1, H2 are in H. But remember that H is closed under the group operation because it is a subgroup. So this is just equal to GKH for all H in H. But that is exactly equal to the coset GKH. So even though this is a true statement, I'd like you to understand exactly why it's true and how we can write it in set notation like that. So with that, we have finished proving this beautiful theorem about the complete characterization of normal subgroups. And that is it. I hope you've enjoyed. If you did, drop a like, subscribe, and share with anyone who would be interested in this fascinating topic. I'll be seeing you all on the next lesson. Have a nice day and bye.